Okay, good evening everyone. I am Shivani Dhok and I welcome you all for the week 10 tutorial for the course of Introduction to Wireless and Cellular Communications. So like every week, this week's tutorial will also be divided into two parts. First, we'll discuss recap of week 10 content, followed by the questions which are related to the week 10 content. You can stop me at any point of time if you have any queries. I request you to unmute yourself and ask your queries because the chat box might not be available to me or rather visible to me throughout the lecture. For any non-technical doubts, you can wait till the end of the session and please do not interrupt in between the technical questions. Okay, so let's start with the recap. So in week 10, we continued with our discussion of CDMA and we were discussing the direct sequence PET spectrum structures. So we were discussing CDMA with the direct sequence spread spectrum. And in that we said that if we want to transmit SI, which is a symbol, so we want to transmit this symbol SI, which may belong to any constellation. So this SI belongs to some constellation. And then we said ki we will transmit U of t, which is SI, under root EB into G of t. And this G of t is in principle, so right now we are considering VPSK. So this G of t is essentially your pulse shaping signal. And this G of t for our CDMA is given by summation Q equal to 1 to capital Q, C of Q into GC of T minus Q times TC So here, this Q is your spreading factor. Then this TC is your chip duration. And your C of Q is basically your spreading sequence. Just a minute, hold on. Yes. Yeah, okay. Yeah, sorry for the interruption. Yeah, so the CQ is your spreading sequence, and this GC of T is basically 1 over root T for 0 less than or equal to T less than or equal to TC. So this is what we had seen earlier as well. Okay, this is just a recap of what we had discussed in the previous lecture, previous week. And after that, we looked at the structures, like how to decode this direct sequence spread spectrum signals. So we can go with either symbol by symbol decoding, or we can go with chip by chip decoding. So these are the two options that we have. I'm not going into details of all of these things, but yeah, we have discussed that in the class. Then we looked at properties of the spreading sequence and how to achieve them with the help of the pseudo-random uh, sequences or pseudo noise. Okay. So the properties of the spreading sequences, we looked at 4 properties for the PN sequences as well. So the first one that we said that it needs to be satisfied is the balance property. What does the balance property say? It says that the number of ones and zeros in a code should be equal to or should be equal approximately. So for an M sequence, so I'm talking about M sequence, which is of the length of 2 power m minus 1. So the balance property says that the number of zeros is equal to 2 to the power m by 2 minus 1, and the number of ones is equal to 2 to the power m by 2. This is the balance property. Then we had the run length property. The run length property says that the number of runs of length I is given by 1 over 2 to the power I into total number of runs. Okay. After that, the third property is the correlation property, or let's say let's first see the shift property. So what does the shift property say? It says that if I have a signal B, a code Bn, and if I XOR it, this is my XOR, if I XOR it with a sequence Bn, another Bk of n, what is this Bk of n? This is shifted signal, shifted version of B by K, or cyclically shifted. Okay, so this is what we have, right? Okay. So if we do this, then what do we get? We get another sequence of the same length, and it is of the same type, but now it is shifted, cyclically shifted by L units. This was the shift property, and this holds, and we have L not equal to K here. Okay, and the last property was the correlation property. And the correlation property here says that the correlation Rx of k is given by 1 over q summation L equal to 0 to q minus 1 x of L into x conjugate of L minus k mod q is minus 1 by q. Now note here, this b here are binary 0 and 1, but here this x's are now mapped to 1 and minus 1. So essentially, generally what we do, we map 0 to 1 and 1 to minus 1. Okay. After we looked at these properties of the sequences, then we looked at another or variations of CDMA. We looked at wideband CDMA, and then we also looked at CDMA 2000. We looked at how we come up with Walsh-Hadamard sequences, and how we, and these are not does not follow the properties of these spread sequences. So in order to make it look like a pseudo random sequence, we scramble them with these PN sequences. And then we looked at CDMA 2000 and other properties. Then we looked at another thing, that is OVSF. This is essentially your orthogonal variable spreading factor. And for this, we looked at a notation where we said that OVSF of L comma 2I. So this is basically of length L, and it is indexed by 2ith code. It is given by, or we can construct it in a sequential manner using the OVSF of length L by 2, which was indexed by I, and OVSF same thing, L by 2 indexed by I. Now if instead of 2I, if we have an odd integer, then we will get, let's say 2I plus 1. Then we will have OVSF of length L by 2 indexed by I and minus of OVSF L by 2 indexed by I. We will see an example of this thing towards the end of the class. Okay. Then we quickly looked at the differences between spreading and encryption. We said that this encryption business is, so in this encryption does not involve expansion of the bandwidth. So encryption does not involve expansion or spreading of bandwidth expansion. And reversing encryption is difficult. Anyone can't do it. You need the proper encryption key to do so. And spreading essentially involves the bandwidth expansion. Then we looked at the very generic Kasami Gold sequences and their relation with the spread spectrum sequences that we have already looked at. So this was all that was covered in this week. If you have any questions till now, then feel free to ask. Otherwise, I'll move on to the questions that I have planned to cover today. Okay. If there are no questions, then let me move on to the next question that I have planned to cover today. The first question for today. So it says that, okay, before I move ahead, I forgot to mention this thing. Yeah, this PN sequences we can construct using the linear shift register representations. So we can use linear shift registers, linear forward shift registers to implement them. Okay, now let me move on to this question. So it says that draw the forward shift register representation for the following polynomial, and the given polynomial is x to the power 7, x to the power 4 plus 1. So given polynomial is x to the power 7 plus x to the power 4 plus 1. So now we need to get the linear shift register representation for this, and this linear shift register essentially has two components. So this shift register representation has two components. The first one is your D flip-flop. This basically leads to some sort of delay. Oh, this is D flip-flop. And the second one is your this. This is basically the adder operation. But for binary, this is equivalent to XOR. Okay, so now first of all, what we need to figure out is how many D flip-flops do we need, and that will be governed by the degree of your polynomial given to you. So the number of D flip-flops is equal to the degree of the polynomial and for our given case the degree of the polynomial is given by 7. So here it is 7. So let me quickly draw them. Five, 6, and we have 7. Yeah, so this is what we have. So this is my output x1. I'll have x2. This is x3. This is x4, x5, x6, and this is x7. So this is essentially nothing but your x to the power 1, x to the power 2, x to the power 3, x to the power 4, x to the power 5, x to the power 6, and x to the power 7. So now what happens is, so this is basically your output. And now if you see, you have x to the power 7. So the polynomial that we have is x to the power 7 plus x to the power 4 plus 1. So now you need to take up these things Like you need to take the output corresponding to x to the power 7, that is this, and output corresponding to x to the power 4. You need to add them and give it as a feedback here. This is how you represent the forward shift registers. So what you will do, you will take a feedback from here, and you will take a feedback from here. You'll XOR them and give them as a feedback as your input. So this is your I. Okay. So this is how you will represent your given polynomial using your forward shift register representation. So what you need to do, you need to take the output of the 7th register and the 4th register, add them. So yeah, add them and feed them back as an input. This is the standard way of representing these things. Okay, any questions till now? If not, then I'll move on to the next. Okay. Okay, so this is the next question. It says that if the initial states of the flip-flops in an M sequence given by the polynomial x cube plus x plus 1 is 1, 1, 1, find the output sequence. So the polynomial given to us is the given polynomial is x cube plus x plus 1, and given initial state is 1, 1, 1. So what do we mean by initial state? So these are essentially the outputs of the flip-flops, the flip-flops. Initial, or rather let me write it in this way. These are initial outputs of the D flip-flop. Now again what we will do, we'll first construct this thing, this forward shift register representation, and then we'll see how exactly the sequence can be constructed. So now here the degree of the polynomial is 3, which means that we need 3 flip-flops. So the output, so what we have here is, let me just paste the same thing, 1, 2, and 3. Yeah. So we have the output of the first one as x1, then we have x2, and then we have x3. And then what we need to do is we need to construct the how XOR gates are connected. So now if you see, the XOR gates are connected between x3 and x1. So we'll have an XOR gate with an input from x1 as well as an input from x3, and this will be feedbacking, or rather feeding back to the input as an input, that is I. So what do we get here? We get that I is given by x1 XOR x3. Okay, and these D latches or D flip-flops, what do they act as? They act as a delay unit. Okay, so let's say at time instance 1, the output of this is 1. So then this will be sent as x2 in the next time instant, that is at time instant 2. So this, at every clock interval or at every clock edge, it will just forward whatever input it has to the next output. Okay, so now let us try to construct what we have. So what is give what all, so the output that we are going to observe is here. So this is our output. So we have x1, x2, x3, and then we have I here, and our I is essentially x1 XOR x3. Let me just, yeah. Okay, okay. So we have this. So let me just do this. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Yeah, so we have this. Now initial thing that was given to us is 1, 1, 1. This is the initial output, and this is given to us. Okay. Now for these values of x1, x2, and x3, what will be the value of I? So the value of I will be basically x3 XORed x1. So we need to do x3 XORed with x1. So this is 1 XORed with 1, which is equal to 0. Okay. Now in the next clock instant, what will happen? So this, at current time instant, this I is input to this D flip-flop. So in the next time instant, this will basically become the output of this D flip-flop. So this I will now become my x1. So now in the next clock instant, or in the second clock instant, what will happen? This 0 or this I will become the output of my first D flip-flop. So we'll get a 1 here. Sorry, a 0 here. Now this x1 was input to this D. So this 1 was an input to this second D flip-flop. So in the second time instant, that will become the output, that is x2 of this D flip-flop. So what will happen? This 1 will get translated here. So we'll get a 1 here. Similarly, this 1 will get translated here. We'll get a 1 here. Now what we need to do? We need to figure out what will be my I. So my I will be 0 XORed with 1. So 0 XORed with 1 will be equal to 1. Okay. Then in the third time instant, same thing. This will get translated here. So we'll get a 1. Then the 0 will get shifted here. You will get a 0 here. And then this 1, this will get shifted here. So you are shifting the values forward. That's why this is known as the forward shift register 1. Now we need to figure out this output. So we'll be having 1 XORed 1, that is input, sorry, I. So we'll have 1 XORed with 1. That comes out to be equal to 0. Now same business we have to do. So we'll get a 0 here. Then this 1 gets translated here. You will get a 1. Then the 0 gets translated here. You will get a 0. And now you have to XOR to get the input. So it will be 0 XORed with 0. This is again 0. So now this 0 will translate here. We'll get a 0 here. Then again this 0 translates here. We'll get a 0. But now this 1 translates here and we get a 1. Now what we need to do for getting I will be x1 XORed x3. So that is 0 XORed 1. This comes out to be equal to 1. In the 6th clock, 1 gets translated here. Then this 0 gets translated here. And similarly, this 0 gets translated here. Now again, you get 1 XORed with 0. And you get a 1. Now what happens? This 1 gets translated here. This 1 gets translated here. And the 0 gets translated here. So now what we have? 0 XORed with 1. So 1 XORed with 0 will be our I, which is equal to 1. And now finally again, this 1 will get translated here. This 1 will get translated here. And finally this 1 will get translated here. Now if you observe carefully what is happening, this was my initial sequence. The same sequence has now started to repeat itself. So now we are getting repetition of the sequence. And what was our output? So where do we measure our output? We measure our output at x3. So this thing, that is from 1 to this part, before the repetition starts, is basically our input. Our output. So the output of this thing is given by 1 1 1 0 1 0 0. Yeah, that's all. Okay, so now this is, so here our m was equal to, so this m was equal to 3, right? So this m was equal to 3, so the length of the sequence is 2 to the power m minus 1, that is 2 to the power 3 minus 1, that is 8 minus 1, which is equal to 7. Okay, so this is what we are getting. Now we just add one more page. So let me repeat it. Output is 1 1 1 0 1 0 0. Length of sequence is 7. Now we had seen that for number of zeros, or rather if we count, the number of zeros come out to be equal to 3, which is basically equal to 2 to the power 3 by 2 minus 1. So here 2 to the power 3 is 8 by 2. minus 1, which is 4 minus 1, which is equal to 3. And the number of ones, if we count, they are essentially 4. Okay, which is equal to 2 to the power 3 by 2. So this is basically 8 by 2, which is equal to 4. Now this we had discussed earlier. This was basically our balance property. Okay, so therefore we can see that the balance property is satisfied. So this discussion is telling us that the balance property is satisfied. Okay, any questions till this point?
Excuse me, ma'am.
Yeah.
Ma'am, you took that 8 clock cycle, na?
Huh?
Hello. There's a
Uh,
go here, ma'am. 1 to 8. The second question.
huh.
Okay, you sort this one. So you have taken that one 8 clock cycles means because of 2 raised to 3 that you have considered, or m is equal to that 3 is there na? Or a
Huh.
x cube is there na? 2 raised to 3 because of 2 into 2 into 2. Because of that only you have considered 8 clock cycles or what? Here I did
Okay.
not get myself.
Yeah. So what I wanted to say here, okay. So this is an M sequence with M equal to 3.
Ah,
And for an M sequence,
ah,
the length of the sequence comes out to be equal to 2 to the power 3 minus 1. That is 7. Okay.
okay.
Now, after
Ah.
7 clock cycles, the sequence starts to repeat. So if
Yeah,
you
yeah, it is
see,
repeated because of this
huh,
XORs.
correct, correct. So now if I go with cycle
Mhm.
9, I will exactly get this sequence. For 10, I'll
Okay,
get
okay.
this sequence. It is not stopping.
Correct.
It will just start go on
Yeah, yeah,
repeat. It start repeating. That's all. That's why I showed it till
correct.
8.
Okay, okay. So because initially whatever we got not, that same we are getting here at eighth
Correct,
instance. Okay.
correct.
So that's why we have
Yes,
to consider 1 to 8.
yes. 1 to 7 is the output. From 8th, it is
1
repeating.
to 7 is the output. Yeah. Okay. Whenever it is repeating means we have to leave it now. We have to stop there only. Okay.
Yes.
I
So length
thought
of the
because yeah, yeah, m is equal to 3. That is there, na? So 2 raised to 3 is there, na? That's why you took 8. I thought this 1 to 8.
no. I just wanted to
No,
show this
okay,
is happening. That's all.
okay, 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 okay. Thank you. Please continue, ma'am.
Yeah, yeah. Okay. Now I think the remaining questions that I have planned to cover today are a little bit similar, apart from one or two. What? So I am not taking memory questions related to CDMA 2000 and all those things. I'm just taking questions which are numerical based. Okay, so let's start with the third question. So what is the bandwidth of a DS-SS system with a spreading factor of Q equal to 64 and symbol time as TS equal to 4 microseconds? So what is given to us is the spreading factor, which is Q equal to 64, and symbol duration TS, which is 4 microseconds. Okay, and what we need to find? Bandwidth of our direct sequence spread spectrum system. So this bandwidth is given by 1 by Tc, where Tc is our chip duration. Now what we need to do is, first we need to figure out Tc in terms of my Ts and Q. Now we know that the symbol duration Ts is nothing but Q times Tc, which means that this Tc is equal to Ts by Q. Now if I substitute this in the bandwidth expression, so what do I get? So bandwidth is 1 by Tc, which is equal to 1 by Ts by Q, which is equal to Q by Ts. Now what was our Q? Q is given to us as 64 and Ts is given to us as 4 microseconds. So this comes out to be equal to 16 into 10 raised to 6 hertz, which is equal to 16 megahertz. Okay, so this is the bandwidth of our DS-SS system. Is it clear?
Yes, ma'am.
Yeah. Just a minute, hold on. Okay. So these are very simple questions. There is actually, it's all related to one formula. Okay. So this question says that what is the symbol duration of the DS-SS system with a spreading factor 64 and chip duration Tc? This is the simplest question. So what is given to us is the spread factor or spreading factor and chip duration so therefore the symbol duration is nothing but Q times Tc, which is equal to 64 into 2 microseconds, which basically comes out as 128 microseconds. Yeah. Same application of same formula. Okay. Till this point, any questions at any point of time? If not, then I'll move on to the next question. Now the next, that is fifth and sixth question, whatever I'm taking is related to the Fourier transform. I know this has been done multiple times, fifth, sixth and seventh, multiple times in signals and systems, DSP and all those courses. But since there was a question related to something related to this in the assignment, so I thought let us take a basic example and then let us look at revisit the proofs of some of the properties. That's all. So let's start with this question. This might be repetition of a very basic concept that we have been using for since lot of time, but still I thought it's good. It's just a good revision to look at it. Okay, so the question says that find the Fourier transform of x of t equal to rect of t by capital T. So how does this rect function look? This rect function looks like this. So it starts at minus t by 2 and ends at t by 2, and in this duration it is equal to 1. Now what we need to do is we need to find the Fourier transform of this. So this x of f is given by integral minus infinity to infinity x of t into e power minus j 2 pi ft dt. Thus x of t is 1 in the range of minus t by 2 to t by 2, which means the integral limits will be valid only from minus t by 2 to t by 2. So therefore this x of f is given by integral minus t by 2 to t by 2 into 1 into e power minus j 2 pi ft dt. This comes out to be equal to e power minus j 2 pi ft upon minus j 2 pi f from minus t by 2 to t by 2. So therefore this x of f is equal to e power j 2 pi f t by 2 minus e power minus j 2 pi f t by 2 divided by j 2 pi f. So this gets cancelled, and what we are left with is e power j 2 pi f t minus e power minus j 2 pi f t divided by 2j. I'll keep here into 1 upon pi f, and this is essentially sine of 2 pi f. Sorry, this is not, this is just pi ft. Sine of pi ft divided by pi f, and for symmetry I'll just multiply and divide by t. So this comes out to be equal to 2 times sine of pi ft upon pi ft. Okay, so this is what we have, and we also write this as t times sinc of ft, where sinc of x is defined as sine of pi x upon pi x. And some people also define sinc in a different fashion. So just a side note, people also define sinc of x as sine x by x. So for this thing, or rather, so this thing will be simply t times sinc of pi ft. So whenever you are referring to different books, you might find different expressions for the Fourier transform of a rect function. So don't get confused. You first go and see how that particular book defines your sinc function, and then you use it. Okay. So be careful. Many people just define sinc as sine x by x, and some people normalize it with respect to pi. Okay. So any questions till this point? Okay. If not, then I'll move on to the next question. In the above question, the first zero crossing of the frequency response occurs at what frequency? And how does it change if we consider x of alpha t for alpha greater than 0? So what is given to us? So we had x of t equal to rect of t by t, and its Fourier transform we saw it comes out as t times sine of pi ft upon pi ft. And at f equal to 0, we can have our limit f tending to 0. This thing comes out to be equal to capital T. So at f equal to 0, this is x of f. X of f tends to capital T. So at x equal to 0, it is not, at f equal to 0, it is not going to be 0. Now the first 0 crossing will occur when the numerator becomes 0 and denominator is not 0. The first 0 crossing will occur for the smallest value of f for which sine of pi ft is 0 and pi ft is not equal to 0. Now sine of x is equal to 0 for all x which are plus minus or rather k times pi, where k belongs to plus minus 1, plus minus 2 and so on. And yeah, it has 0 also, it includes 0. 0 plus minus 1 plus minus 2 and so on. So the smallest value of k, let's consider the positive value. So the smallest value of x or let's say positive value of x, smallest positive value of x for which sine of x is equal to 0 is x equal to pi. So now we'll use the same logic. So using this logic, the smallest value of f, smallest positive value of uh, pi f into t will get when that the pi f into t is equal to pi. So using this, the smallest value of f for which x of f is equal to 0 is given when pi f into t is equal to pi. So this gets cancelled. So you have f equal to 1 by t. So how does your sinc function look? So your x, magnitude of x of f, it looks like it starts at t. Then at 1 by t you get a 0. Then at 2 by t you get another 0. And so on. And if you just plot x of f, it looks something like this. So this is your f equal to 1 by t, the first 0 crossing. Is it clear? Any questions? Okay. Now this was the first part of this question. Now the second part says that how does the zero crossing change if we consider x of alpha t if alpha is greater than 0. So this was the first question. The second part says that, or the second part is, what it asks you is, what is the zero crossing, or the first zero crossing of x of alpha t when alpha is greater than 0. So for that, what we'll do is we'll first look at the scaling property of Fourier transform or time scaling property of Fourier transform. So if x of t has a Fourier transform of x of f, then x of alpha t has a Fourier transform, let's say x tilde of f, it is what? And we'll consider alpha greater than 0 for this question. So this x tilde of f is given by integral minus infinity to infinity x of alpha t into e power minus j 2 pi ft dt. Now what we'll do, we'll substitute alpha t is equal to some t1. So this t is equal to t1 by alpha, which means dt is equal to dt1 by alpha. So therefore this x tilde of f now becomes integral minus infinity to infinity x of t1 into e power minus j 2 pi f t1 by alpha into dt1 by alpha. I can rearrange this as x tilde of alpha is equal to x tilde of f is equal to 1 over alpha integral minus infinity to infinity x of t1 into e power minus j 2 pi. I'll write this ft1 by alpha as f by alpha into t1 into dt1. Now this integral here is nothing but Fourier transform of x of t evaluated at f by alpha, that is x of f by alpha. So therefore this x tilde of f is nothing but 1 by alpha into x of f by alpha. So this is a generic property that we have just seen. So now we'll use this property for our case. So for us, x of t was rect of t by capital T, and x of f, we had seen that it comes out to be equal to t times sine of pi ft upon pi ft. So, and yeah, this is what we have. So x of alpha t is nothing but rect of alpha t by alpha little t by capital T, and we get x tilde of f as 1 by alpha into x of f by alpha. So therefore this x tilde of f is given by 1 by alpha into x of f evaluated at f by alpha. So it becomes sine of pi. F is now f by alpha capital T divided by pi f by alpha into capital T, which is equal to, this alpha gets cancelled, so we have sine of, we have a capital T here, sine of, or rather T times sine of pi ft by alpha divided by pi ft. Okay, so this is what we have right now. Now again we need to find the zero crossing. So the smallest zero crossing will occur when sine of pi ft by alpha is equal to 0 and pi ft is not equal to 0, which implies that this pi ft by alpha should be equal to pi, which means that this, so this pi gets cancelled, which means that f is equal to alpha by t. Okay, now this alpha is a positive quantity, we have already seen. So now what happens is, what I'll do is something like this. I'll draw both the cases. So let's say I have 1 by t, 2 by t, 3 by t, and so on. And yeah, so magnitude of x of f was, we have a t here, it goes to 0 at 1 by t, and so on. Something like this we have. Okay, now yeah, this also I'll just rearrange it a little bit. I'll just multiply and divide by alpha. Yeah, like this. Okay. Now what I'll do, I'll first take alpha equal to 2. So if I have alpha is equal to 2, so what I'll get is the zero crossing will first now occur at 2 by t, then we'll have 4 by t here, and the magnitude will be t by alpha. So for this first zero crossing at 2 by t, and magnitude will be equal to t by alpha, that is t by 2. Okay, I'll just change it a little bit. I want t by 2 to be there. Yeah, t, so it goes like this. So now this, for alpha equal to 2, it starts with t by 2, and the first zero crossing occurs here, the second zero crossing occurs here, and so on. So this is for, this one is for alpha equal to 2. And if I have alpha equal to half, then first zero occurs at alpha by t, so this will be at 1 by 2t, then it will be at 1 by t, and so on. And magnitude is t by alpha, so t by 1 by 2, so that becomes 2t. So we have 2t here, then we have 1 by 2t, Then we have 3 by 2t and so on. So it starts something like this. Then we have a jump here. And so on. So this one is for alpha equal to half. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. This is also related to Fourier transform. So the scaling property, time shift property, I am deliberately taking because this will help you a lot in solving or understanding the Fourier transform of your pulse shaping filter in your CDMA. So that will help you to look at its properties, how the spreading occurs, and all those things. Okay, so now it says that prove the time shift property of the Fourier transform. So what is the time shift property? So if I have a signal x of t, and let's say it has a Fourier transform of x of f, then if I shift this by a factor of, let's say, t naught, then what is the Fourier transform of the signal? Like, let's say x tilde of f, or let's say x bar of f. Okay, so by definition of Fourier transform, this x bar of f is given by integral minus infinity to infinity x of t minus t naught into e power minus j 2 pi ft dt. Yeah. Now what I'll do, I'll replace, or I'll substitute t minus t naught as some t1. So I have t equal to t1 plus t naught. So dt is equal to dt1. And the limits remain unchanged. So therefore, x bar of f is now integral from minus infinity to infinity. We have x of t1 into e power minus j 2 pi f. I have to replace this t by t1 plus t naught dt1. So this I can write as integral minus infinity to infinity x of t1 into e power minus j 2 pi f t1 into e power minus j 2 pi f t naught dt1. This is a constant. I can take it outside the integral. So this is basically e power minus j 2 pi f t naught integral minus infinity to infinity x of t1 into e power minus j 2 pi f t1 dt1. And we know that this thing is basically Fourier transform of x of t, that is equal to x of f. So therefore x bar of f is equal to e power minus j 2 pi f t naught into x of f. Is it clear? Any questions? Okay, if not, then I'll move on to the next question. Okay. So this question says that if the chip rate is 1.2288 into 10 raised to 6 chips per second and the data rate is at least 1000 bits per second, then find the processing gain. So the processing gain is nothing but your Q, that is your spreading factor. Now this chip rate is 1 by Tc, where this Tc is your chip duration, and this is given to you as 1.2288 into 10 raised to 6 chips per second, and the data rate, which is 1 by Ts, where this Ts is your symbol duration, consider your binary a BPSK kind of situation. So this is 100 bits per second. Okay, so now what we need to do is we need to find the value of our Q. Same story, your symbol duration Ts is given by Q times Tc. Now all the things that I have are in terms of 1 by Tc, 1 by Ts, and so on. So what I'll do, I'll take the reciprocal in both the sides. So I'll get 1 by Ts is equal to 1 by Q into Tc. So this Q now becomes 1 by Ts upon 1 by Tc, or in other words, what I'll do is I'll write this as data rate is equal to your chip rate upon Q. So therefore this Q becomes chip rate upon your data rate. So this chip rate is given to us as 1.2288 into 10 raised to 6 divided by the data rate is given to us as 100 bits per second per hertz. So this becomes 1.2288 into 10 raised to 4, or rather 12.288 into 10 raised to 3. So this is basically your processing gain. Is it clear? Any questions?
No, man.
Yeah. Okay. If there are no questions, then let me move on to the next question. So this is also like the CDMA questions are generally very simple to solve. It all revolves around the same formula or some properties or the four properties of your PN sequence that we have already discussed earlier. Okay, so now this particular question says that calculate the number of ones and zeros in the sequence for in the basically in your M sequence for the following cases. That is when M equal to 5 and when M equal to 3. So this is nothing but the use of your balance property. So this is simply use of the balance property of the PN sequences or the random sequences. Okay. So again, I'll just reiterate what was the balance property. So for an M sequence, the number of zeros in the sequence is given by 2 to the power M by 2 minus 1, and the number of ones in the sequence, I think I wrote it in a different way, wait. Yeah, so zeros is to the power M minus 1. And ones is 2 to the power M by 2. Or this I can also write as 2 to the power M minus 1 minus 1. And this is 2 to the power M minus 1. Okay. So now let us do it for the two cases that we have. So the part 1 is M equal to 5. So therefore, for this number of ones is 2 to the power 5 minus 1, which is nothing but 2 to the power 4, which comes out to be equal to 16. And number of zeros, this is 2 to the power 5 minus 1 minus 1, that is 2 to the power 4 minus 1, which is 16 minus 1, which is basically your 15. And similarly, we have part 2, and this is for M equal to 3. So for this number of zeros, number of ones is 2 to the power 3 minus 1, that is 2 to the power 2, which comes out to be equal to 4. And number of zeros is 2 to the power 3 minus 1 minus 1, which comes out to be equal to 2 to the power 2 minus 1, which is 4 minus 1, which is equal to 3. So this M equal to 3 we had already seen in the earlier part, that is question number 2, where we had generated the PN sequence for the given primitive polynomial. Any questions till this point?
now.
Yeah. Okay. So the next question is again a simple question. It says that construct an 8x8 Walsh-Hadamard code and identify the predecessors and successors. So first I'll just give how the Walsh-Hadamard code is constructed, and to identify the predecessor and successors we'll use this OVSF kind of structure. This structure that we had seen no for OVSF. So we'll use this particular structure to get it. Okay. So first I'll just show how the Walsh-Hadamard sequences are constructed. Okay. So we want 8x8 Walsh-Hadamard sequence. So first we'll construct the first H1, which is basically, or let's say H0, we'll start with H0, which is basically simply your 1. Then this H1 is given by H0, H0, H0 and minus of H0. So this comes out to be equal to 1, 1, 1, minus 1. Now this H of 2 is nothing but H1, H2, H1, H1, H1 and minus of H1. So this comes out to be equal to 1, 1, 1, minus 1. Then we have 1, 1, 1, minus 1. Again H1 repeated, 1, 1, 1, minus 1. And then we have minus 1, minus 1, minus 1, 1. And finally this H3. This H3 is given by H2, H2, H2 and minus of H2. So I'll just copy paste this on next slide. So we have H2, so it is 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1, minus 1, minus 1, 1 minus 1, minus 1, 1. Yeah. Then the same thing repeats. 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1, minus 1, minus 1, 1 minus 1, minus 1, 1. Then we have 1, 1, 1, 1, 1, 1, minus 1, minus 1, 1 minus 1, minus 1, 1. And now the negative of it. So we have we have negative of it. So minus 1, minus 1, minus 1, minus 1. Then minus 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, 1, minus 1. So this is the 8x8 Walsh-Hadamard matrix. We take each column of this matrix and treat it as a code, and then to avoid or to satisfy those properties of random sequences, we scramble them with PN sequences. Okay. So this was all about how to construct the Walsh-Hadamard code. This is one way of doing that. And another way of doing the same thing was treating them as your OVSF structure. So for that, what we had seen, so we'll construct or we'll see approach to. And in this approach to, what we have, this OVSF of length L and indexed at 2I, it is given by OVSF of L by 2, I, and OVSF of L by 2, I. Then this OVSF of L, 2I plus 1, it is given by OVSF of L by 2, I, and minus of OVSF L by 2, I. Okay, so this is what we have. Now what we'll do is we'll start with L equal to 1, capital L equal to 1. So for L equal to 1, what do we have? We will have 1. Okay, I'll do it in this way. 1. So this is basically OVSF of 1, 1. Now this will branch out into 2. So the first one here will be OVSF of 2, 1, and the second one will be OVSF of 2, 2. Now if we have OVSF of 2, 2I, that is this one, what we do, we repeat the same thing 2 times. Okay, so this thing will be simply OVSF of 1, 1, OVSF of 1, 1, which is simply repetition of this quantity 2 times. So we'll get 1, 1, and here we'll get 1, minus 1. So what do we have? This one is basically OVSF of 1, 1, minus of OVSF of 1, 1. And this thing here is nothing but OVSF of 1, 1 and OVSF of 1, 1. Okay. So now what we'll do, we'll again branch it out into 2. Yeah. So we'll branch it out into 2. Like this. Yeah, okay, so my mistake, this indexing starts from 0. so this has to be done in another other way round. Yeah, that's all. Yeah. Then we'll have here, yeah, indexing always starts with 0 in our case, maximum times. Yeah, here we'll have OVSF, we'll have 4 comma 0, OVSF 4 comma 1, then we'll have OVSF 4 comma 2 and OVSF 4 comma 3. So for OVSF 4 comma 0, what we have to do, we have to repeat. So we'll get something like this. So this thing here will be basically OVSF of 0, 0, 0, 0. Yeah. OVSF of 2 comma 0 comma OVSF of 2 comma 0, and we'll have to flip the sign here. So what we need to do is, first we will just repeat 1 1 1 and 1. So this is the first one, and then we'll repeat the first part as it is, and then we'll change the sign afterwards. Similarly here, first we'll repeat it as it is, and then we'll flip the sign. So this is of length 4, and now we'll again split it into 2. I'll remove this part for space. This also, I don't want it here. Yeah, like this. The last one is this. So this is 8 length. So here I'll have OVSF of 8 comma 0, OVSF of 8 comma 1, OVSF of OVSF of 8 comma 2, OVSF of 8 comma 3, 8 comma 4, 8 comma 5, and the last one is OVSF of 8 comma 6 and OVSF of 8 comma 7. Yeah. So the last ones that we get here is 1 1 1 1, and same thing repeated. And for 8 comma 1, the first one is as it is, but for next we flip the signs. Then for this one, we repeat it 1 1 minus 1 minus 1, 1 1 minus 1 minus 1, and this is 1 1 minus 1 minus 1 minus 1 minus 1 1 1. Here we have 1 minus 1 1 minus 1, and same thing repeated 1 minus 1 1 minus 1. However, for the next one, we'll first repeat it as it is, that is 1 minus 1 1 minus 1, and we'll flip the sign minus 1 1 minus 1 1. Now for the sixth one, we'll have 1 minus 1 minus 1 1, and same thing repeated 1 minus 1 minus 1 1. And for this, we'll have 1 minus 1 minus 1 1, and now the signs will change minus 1 1 1 minus 1. So this is how we'll construct the codes with the help of that OVSF structure. Is it clear till this point? Any questions? So now the other part of this question was to identify the predecessor and successors. So now if you consider this particular code, that is the last one. So all of the codes that lie in this line, these are their predecessors. So, and all of these codes which don't lie on that line are not their predecessors. Similarly, here for this particular code, this is the predecessors and this is the successor. But these are not their predecessors. This is also their successor. These are also not their successors. And this is not the predecessor. Does that make sense? Any questions till this point? So for this particular code, what are the predecessors? The predecessors are this one and this. And these are not. And for this particular code, these two are the successors. Any questions till this point? If not, then this was the last question that I wanted to cover today. If you have any queries, then feel free to ask. Otherwise, you're free to leave the meeting.
Okay, ma'am. Thank you. Thank you very much.
Thank you. Thank you for attending today's session. Hope you attend the next session as well. Thanks.